Hi guys, my name is Kumar Gandharv. I'm an application and systems engineer in Infineon, America. I work out of the Rhode Island Warwick site. Currently, I'm working with the point of load group here, and I'll be one of the technical directors for this capstone project. I also have with me Yong, who is the second technical director.
Hey guys, my name is Yongzhou. I'm an application and product definition engineer here in Rhode Island Design Center of Infineon Technologies. So I'm working on next generation power station and module product. I'm very glad to be your technical director on this capstone project, and I look forward to working with you soon.
Hey guys, this is Kumar here. For today's presentation, we will be dividing the task between me and Yong. I'll go through the agenda. Basically, we'll be going through the company profile and then what the Rhode Island Center does. I will also talk about the motivation behind the project and then the anticipated best outcome. And then my colleague Yong will go through more details into the circuit representation, the GUI example, the microprocessors that you guys will be using, which is from Cypress, and then what are the skill sets that you will need to be successful with this project. Infineon Technologies is a semiconductor company and it's a global company. We make products that make our life easier and safer. We have around 42,000 employees worldwide, and last year we did a sales of around 8 billion euros. Now, the Rhode Island Center designs and conceptualizes power management ICs or products that power up the digital world. You can imagine a CPU, a GPU, and our ICs would be there paired with that to power it up. And the application could be from servers to AI to consumer products and mobile communications. The work being done in Rhode Island is primarily divided into three categories. So we do digital controller, uh, and then point of load, and also the power stages. So as I mentioned, the products done out of here are mostly used to power up the digital world. Basically, we power up the CPUs and the GPUs, the heart of every product, and what they require is current to work efficiently and when they need it. So basically, what we do is before a product goes from or an IC from Rhode Island Design Center goes on an actual product, it needs to be thoroughly tested so that we can make sure that it meets all the needs of the CPU. So you can see on the screen that I have a graph of a current ramping up from Imin to Imax level, and then it ramps up with a defined slew rate. Now this could be a current or load profile for any particular processor. Now what also comes with that every processor manufacturer will specify the overshoot or the undershoot that the processor can withstand and still continue to operate in its normal condition. So the overshoot and undershoot are basically voltage excursions that are seen from the nominal value as the current ramps up or ramps down. And by the normal operation of the CPU, I mean beyond that, this could result in a CPU being reset, and you, in a physical world, you see that as in the form of, for example, like a blue screen. So we would want to avoid that. So that's why this thorough testing of our products is necessary to see that if we meet all the specs. To do that, what we utilize is something called as a load slammer. Now, the load slammer is something that mimics a CPU performance and helps us to emulate the actual CPU even before a CPU is being used. So in order for this load slammer to work, we create this elaborate setup and then we go through run these tests, which we call as 3D transient tests, and look at all the results that we get out of it. right now we use a function generator to control the mini slammers or the load slammers that we use. There is this additional equipment that has to be used, and first of all, it's not repeatable because depending upon what equipments or what set of equipments you are using, the results vary, and there is no good graphical user interface. So in order to overcome these is what prompted us to come up with this definition for the project, where we wanted you guys to help us with this load slammer. The load slammer that we are thinking about, or we need your help on, has to be flexible so that you can do basically it needs to have an onboard programmable load controller where you can program anything that you want on the microcontroller itself. It should not need an external function generator that will help us with the cost saving. And it should be repeatable because many a times we need to look back at the data that we took, let's say 3 months ago, and if you don't have the exact same equipment, it's very hard to replicate it. The test has to be robust. During the testing, there has to be some sort of current feedback and telemetry that will help us know that what we're doing is correct. And let's say if anything is going wrong, it will help us protect the product and the load slammer itself. It should be easy to use. Doesn't matter how good your hardware is, if you don't have an easy way of using it, not many people will. And we want to make sure that this product is being used by as many people as possible. So we would like to have a good GUI. The GUI definitely should be easy, and it should have a nice clean interface that will help us basically increase the usability of this load slammer.
So what you see here is a demo board for our POL products. This black IC on which I'm pointing, that's the product that we are testing. It is being used in a synchronous buck topology. These two terminals are the 12 volt input, and these two black connectors are what we use to simulate transient conditions. This is part of the LC filter that is put at the output of the buck converter, and this loop of wire is what we use to measure the current going through this LC filter. Now what you see here is an actual demo that is running right now. So these are the two mini slammers or the loads that will simulate a transient condition for the POL product. You have this loop of wire. This is a current probe that is being used to measure the current through the inductor. The two mini slammers are being controlled by this control board, which gets its input from this function generator. Now this working of this is, in short, is that this function generator sends out an output to this control board, and the control board is controlling both of these two mini slammers synchronously, and then I can control, give it a load step, which will be seen by the POL device. Now I will enable the part, and as you can see on the screen, channel 7 of the pink curve is basically the output of my control board, and the yellow curve is the current through the inductor. Now if I zoom into this, you can clearly see that the mini slammers are simulating the condition for a transient, wherein it is doing a current step from this level to this level. Now based upon this, what we do is we try to measure, the blue curve is the output of this converter, and through this test we are trying to measure the undershoot, which is the dip in the output voltage, and the overshoot, which is the peak in the output voltage. And basically we are doing this because for every product that we do, if it is being used as part of a bigger system that has a CPU, the CPU has a spec for overshoot and undershoot that we have to meet. So this test is very important to us. And as you can see from all the equipments that we are using here, it's a fairly complicated setup that we have to do before we can do this test. And this is what that we are trying to simplify through the project. Thank you.
These are some of the anticipated best outcomes that we have come up with. So we have tabulated it in the form of a table. I'm not going to go through each one of them, but let's just pick one of them. So like the max current. So 50 ampere is the minimum current that we want as for the max limit. Now, if you guys come up with a design that allows you to do more, I mean, that's well and good, but that's the bare minimum that we want for the min current. The load slammer should have the capability to support both DC loads and to have a capability of programmable load profiles. We should be able to calibrate the load current by utilizing the current feedback, thereby removing the need for manual tweaking. Basically, we don't want to tweak our setup every time we use a different set of equipment, or we do it after a duration of time. So we want it to be consistent. The load profile should be able to we should be able to store the load profiles on the onboard microcontroller itself. I have mentioned that before. That just helps us with the ease of use and robustness part of it. And the GUI should also allow the user to create a piecewise linear model. So basically, the current profile that I showed you before, if needed, the user should have the capability to create that on his own, and then he should be able to save that profile on the microprocessor board, on the onboard microprocessor. It should be self-contained, so that there is no special need for a special equipment or a driver. Basically, it should be in the form of like an executable file where everything is everything is encompassed into that package, and you just need that package to run the GUI. There shouldn't be any need for special drivers. And then it should be easily transportable between different compute platforms. So it shouldn't be limited to just one platform. It should be allowed to go propagate to multiple platforms.
This is a simplified circuit schematic with 50 amp rated voltage regulator and the electronic load for transient testing. The node transient current is provided by high current MOSFET and the series no ohmic resistor. The closed loop control is implemented with op-amp, which drives the MOSFET gate to source voltage such that the feedback current sense voltage is equivalent to the reference signal. Ideally, we would like the actual transient current to follow the reference signal without any delay, but in reality, this is difficult due to the op-amp bandwidth and microcontroller ADC sampling rate limitations. So this is a good topic to look into in order to optimize OO system design. This slide covers the GUI examples and the list of features that we are looking for. The goal is to make it easy to control the load current profile and process the data. On top of that, system monitoring and fault protections are also designed to make the OO system more robust. There are two GUI examples on the left-hand side, which look quite different, but they all have similar functionalities and features. The picture on the right shows the 3D plot of test data, which is generated automatically when the test is completed. Since we do the transient test almost every day, the amount of test data is also quite big. Therefore, we are thinking of creating a database to store and manage all the test data in a standard format. Definitely, there are more improvements and features that could be added, and we encourage you to implement them into the GUI if you have any good idea. In this project, Cypress PSoC5 microprocessor will be utilized as the test platform. It is based on ARM Cortex-M3 CPU core with lots of hardware resources. It has maximum 80 MHz operating frequency. The fast ADC samples the signals with minimum delay. The 256 KB flash enables the user to store current configuration files. There are also plenty of GPIOs
which could be configured to monitor system operation or issue system alerts. You could also click the link in the table if you would like to find more information about PSOC5 microcontroller. In order to best practice social distancing, Cypress PSOC5 development kit will be available for the candidates for system design and programming in UI lab. Infineon will provide a node board system to optimize hardware interface. The final system prototype will be validated both in UI lab and Infineon. Overall, this is a good opportunity for hardware-software co-design. To make the capstone project successful, we would need help from both electrical engineer and computer engineer. As an electrical engineer, you should have knowledge in analog circuit, digital logic, and feedback control theory. It is better if you are also familiar with microprocessor and SPICE simulation. As a computer engineer, you will fit into this project if you are familiar with graphic interface architecture and data management. Python is preferred as it is easy to use, but you could also select other programming language which works best for you. Besides the programming skills, some knowledge in analog circuit and control theory will be a plus. Beyond the scope of this project, I've also listed some of the wish lists that I believe are challenging but good to have. The first wish list is to create a database which stores the new transient test data in a standard format. The second wish list is to utilize machine learning algorithm to predict the worst case transient by searching similar test data stored in the database. This is definitely a fun project, and I look forward to working with you soon. Thank you.